Hello all. In this video, we will see two more problems on Laplace and Poisson's equation. So, given problem is two plates of parallel plate capacitors are separated by a distance d and maintained at potential 0 and V0. Assuming negligible fringing effect, determine the potential at any position between the plates, b. the surface charge density on the plates, c. the capacitance between the plates. So, I will draw the two parallel plates. So which these plates are parallel to xy plane. These plates are parallel to assume that these plates are parallel to xy plane. So one is at z is equal to 0, other one is z is equal to at z is equal to d. Because the distance between the two plates are given as d. So I am drawing two plates in xy plane, and the first place is placed at 0 and other place is placed at z is equal to d, and distance between these two plates is taken as d. And they are also given that the potential at two plates are maintained, one is at 0, other one is at v0. So the plate at 0, that is z is equal to 0, I am considering the potential at that plate is 0, and the plate at d, that is z is equal to d, I am considering the potential at this plate as v0. Now we have to find what is the potential between the two plates. So we have to find what is V, equation for V between two plates. So next you have to find what is surface charge density, rho s. Then you have to find what is the capacitance. So first, using Laplace equation, we will find what is the potential equation between these two plates. Here, if you observe, these plates are placed in xy plane, which means the normal component to this plane is z component. So we have only z component in the potential equation because it is parallel to xy plane. The normal component for this is z. So we have only z component in the potential equation. So we know that Laplace equation, which is written as del square V, which is equal to 0. In Cartesian coordinate system, we can write del square V, which is equal to dou square V by dou x square plus dou square V by dou y square plus dou square V by dou z square, which is equal to 0. But here, as I told, it's a parallel to xy plane and normal vector is z axis. The normal vector to this plane is z. So we have to consider only z component here. So I can write dou square V by dou z square, which is equal to 0. Now to find V, I have to integrate twice because this is second order differential equation. To find V, I have to integrate twice. So if I integrate once, I will get dou V by dou z, which is equal to integration of 0 plus integration constant C1. So I can write dou V by dou z, which is equal to C1. Now, to find V, we have to integrate one more time. So integration of dou V by dou z. So that will be integration of C1 with respect to z plus C2. That is the integration constant. So integration of constant into dz will be the C1 into z plus C2, which is equal to V. So to find what is the C1 and what is C2, so we know the boundary conditions given here. That is, at z is equal to 0, V is equal to 0, and at z is equal to d, V is equal to V0. Now, at z is equal to 0, V is equal to 0, and at z is equal to d, V is equal to V0. Substitute z and V in the equations. So once substitute z is equal to 0, then V is equal to 0, and other time substitute z is equal to d and V is equal to V0. Now, if I substitute z is equal to 0 and V is equal to 0 in this equation, we will get 0, which is equal to C2. So C2 is equal to 0. Now we know that one more equation is V1 V0 into C1 into D plus C2, because Z is equal to D and V is equal to V0. So substituting that, you will get V0 is equal to C1 into D plus C2. But from this equation, you know that C2 is equal to 0. So substitute that, you will get C1 is equal to V0 by D. So C1 is equal to V0 divided by D. So substituting both in this equation, you will get C1 is V0 by D and C2 is 0. So substituting that, you will get V is equal to V0 into Z by D volts. Now, this is the first question, equation for potential between the two plates. Second question, we have to find surface charge density. To find surface charge density, we have to find what is electric field intensity. So we can find electric field intensity by using the relation between potential gradient and electric field intensity. So that is E is equal to minus del V. But V has only Z component. So in the del V equation also we have only Z equation, that is minus dou V by dou Z into AZ cap. So if you integrate this, you will get, sorry, if you differentiate this, you will get minus V naught D into AZ cap volt per meter is the electric field intensity. Now from electric field intensity, I can obtain electric flux density using the relation D is equal to epsilon into E. So D is equal to epsilon into E. So E is minus V naught by D into AZ cap. So substituting that, we will get minus V naught epsilon by D into AZ cap coulomb per meter square. Now, as I told in the previous problem, so we will consider this flux density is not have only normal component, which is a perpendicular to the surface. So at that case, if the total flux density is equal to normal component of flux density, then the normal component of the flux density is equal to surface charge density, the magnitude of the surface charge density, because always the flux normally flowing outward from the surface is equal to the surface charges, the density of the surface charge present in that area. So we can say the normal component, magnitude of normal component is equal to the surface charge density. So I can write rho s, which is equal to magnitude of d, because here I am considering the flux density is normal to the surface, so it has only normal component. So I can write rho s is equal to magnitude of d, which is equal to magnitude of d. So which is equal to V naught into epsilon into d. Minus is will give the direction, but I need to consider only magnitude. So that's why V naught epsilon by d here. Now, so this is surface charge density. What is the next question? You have to find capacitance. To find capacitance, we have to know what is the potential difference between two plates, and other thing is what is the charge at between two plates. So to find the charge between two plates, we can use the Q is equal to surface charge density into area. So area of the plate is, if we take A as the area of the plate, so we don't know what is the length of the plate, so we can't find what is the area. So we will assume here A is a cross-sectional area of the each plate. And so if you see this diagram, the potential at this point is V and potential at this point is V naught. So potential difference between these 2 points is V naught minus 0. So potential difference is V naught between the plates. So I can write, so the potential difference between two plates as V naught. Now I know what is Q, now I know what is V naught. So substituting that in the equation for capacitance, I will get equation for capacitance. You know that C is equal to Q by V, where Q is rho s into A and V is V naught, and so you will get rho s into A divided by V naught. So V naught, rho s is V naught epsilon D. So substituting that, you will get V naught epsilon into A divided by D V naught, which is equal to V naught get cancels. So you will get the equation for parallel plate capacitance as epsilon A by D farads. So this is the equation for capacitance for a two given parallel plates. So this is how you find the capacitance of given system. First you have to find what is the potential between them. Then using a potential gradient equation you can find E. So then you can find D using the relation between D and E. Then you can find what is rho s, assuming that flux density is normal. So then the magnitude of the flux density is equal to surface charge density. So once you get the surface charge density, you can find the charge, that is rho s into area. Then you can find, you know that the potential between the plates. So substitute that in the equation for capacitance, you will get the what's the value of capacitance. So we will solve one more problem on this. So next problem is, there exists a potential of V is equal to minus 2.5 volts on a conductor at 0.02 meter, and V is equal to 15 volts at R is equal to 0.35 meter. Determine E and D by solving the Laplace equation in spherical coordinate system representing potential system. So here V is equal to minus 2.5 volts at R equal to 0.03 meter and V is equal to 15 volts at R equal to 0.35 meter. These are the boundary conditions they have given. Now you have to find E and D. So using Laplace equation. But to find E and D, you have to know what is the V. So to find V, I'll use Laplace equation. In spherical coordinate system, I can write Laplace equation as 1 by r square dou by dou r into r square dou v by dou r, which is equal to 0. So if I take r square this side, so I'll get dou by dou r into r square dou v by dou r, which is equal to 0. So to find V, I have to integrate twice. So I'll integrate once, then I will get one integration constant C1. So that is r square dou v by dou r, which is equal to C1. Similarly, to get V, I have to integrate one more time. So if I integrate this equation and R I will take this side, then I will integrate this equation. So I will get V is equal to minus C1 by R plus C2. So these C1 and C2 are the integration constants. Now substituting this given condition, that is V is equal to minus 2.45 volts at 0.02 meter and V is equal to 15 volts at R is equal to 0.35 meter. So substituting both initial conditions, you will get two equations. So here in this, once you will substitute minus 2.5 and R as 0.02 meter, and other time you will substitute R is equal to 0.35 and V is equal to 15 volts. So you will get two equations. Solving these two equations, you will get, that is minus 2.5 is equal to minus 50 C1 plus C2, which, and one more equation is 15 is equal to minus 2.8714 C1 plus C2. So these are the two equations. Solving this equation and this equation, you will get C1 as 0.3712 and C2 as 16.0606. Now substituting the value of C1 and C2 in this equation, so you will get V is equal to minus 0.3712 by R plus 16.0606 is the equation for potential. So once you get the equation for potential, now you can find what is E using the relation between E and D, that is minus del V. E is equal to minus del V. So here we assumed only radial component, so it is equal to minus dou V by dou R into AR cap. So we know that V, that is minus 0.3712 by R plus 16.0606. So integration, the differentiation of this 16.0606 is 0 and integration of 1 by R is, differentiation of 1 by R is 1 by, it will become minus 1 by R square. So this will be 0.3712 by R square into A R cap volt per meter E. So we know that relation between D and E, that is D is equal to epsilon into E. So epsilon R and epsilon naught are not specified, which medium they didn't specify. So we will keep as it is. So we can write minus 0.3712 epsilon naught into epsilon R by R square into A R cap. So this is the equation for. So you can simplify this by substituting epsilon naught as 8.854 into 10 to the power minus 12, or you can keep as it is here. So here what we did is, we have to find what is E and D, so for the given potential conditions. So and they given that it is in spherical coordinate system. So we will assume that, so it has only the radial component. So we will have del square V can be written as 1 by R square dou by dou R into R square dou V by dou R, which is equal to 0. So we will integrate twice. We will get two integration constants C1 and C2. So we will get equation in terms of C1 and C2. So after substituting boundary condition, we can obtain what is the value of C1 and C2 by solving two equations. For boundary condition 1 and for boundary condition 2, you will get corresponding two equations. You will solve that and you will get C1 and C2. Once you get the C1 and C2, substitute the value of C1 and C2 in the potential equation, in this equation. Then, so after getting the potential equation, so to find electric field intensity E, so use the relation minus del V. And we also assume that the V has only radial component, so we have only dou V by dou R into AR cap as del V. So substituting V and differentiating this, you will get. So once you get E, so to find D, so you can use relation of D and D is epsilon E. So substitute, and that is the equation for D. So this is the how to find the E and D using the Laplace.